I know some of you probably have seen it before. I think it is this one, right? Yeah. So basically, as we are moving the points or moving one, you can see simply you are guiding one motion, and the whole robot is responding by adjusting the posture, balancing, and doing all of these things, in fact, without any knowledge of trajectory or the joint position that it needs to take. Well, this is also illustrates how we are able to, in fact, decouple these. So if I change the posture, if I pull on the hair, you can see the task is not moving. And this is done in this system that we developed, where you can start to integrate constraints like joint constraints. If we make the robot fall, it goes through all the constraints of the joints. But if we put those joint constraints, it's going to hit the constraints, and it will basically collapse with those constraints that can be represented in the system. So what was interesting was that as soon as we did this analysis, we realized, well, this is not only useful for robots, this is useful to study human motion, especially to study high performance motion. So we started to work with our athletes at Stanford, capturing the motion, trying to analyze how we are moving, how we are throwing, for instance, what are the characteristics, and how this is taking place. Now, what you observe, you remember this quadratic form. Well, phi, if you take the ellipsoid, you see that we are walking through the minimum axis of that ellipsoid. Better, you know, in robotics, we look at the ellipsoid of phi, so the direction of the minimum of the characteristics of phi along the eigenvectors. You have the magnitude of the directions of phi, and you will see moving along the minimal axis, which is minimizing phi even in dynamics as you are moving. But more interestingly is that think about the capacity of the robot. You're going from torque to accelerations. Given your characteristics, your torques are going to, for each of the joint, are going to produce those acceleration capacities. So, for instance, for the Puma, to accelerate in this direction, you have much less ability than to accelerate in that direction. The Puma is capable of accelerating in those directions. Now, the human, well, we have the same or similar characteristic that we can determine. And now we can see, in fact, along that trajectory, we are moving along the maximum acceleration lines. That's why we don't move in straight lines. We are moving, we learned how to discover and find those maximum acceleration as we it's coming and going back. Okay. So now what we can do is we can analyze characteristics, and are subject dependent. So for each subject we have to find the own characteristics. It's not only something that is common to everyone, because it depends on the muscle capacity, it depends on the physiology, and we can start to build atlases for a specific subject, and then we can teach them how to move for their own, with respect to their own physiology. So we are analyzing motions in golfing, or in the different high performance motions. But what you need, if you want to feedback to the human through stimuli corrections on the motion, you really need to be able to do the tracking of the motion and resolving of the dynamics in real time. So this concept that we saw earlier about decomposing task and posture was used in a hierarchical decomposition allow us to control the robot in the marker space. If you are able to control in real time the robot in the marker space, that is to move, not the robot, the human model in the marker space, you're going to able to match the marker motion, and that means you will be able then to create, to resolve the dynamics. So here is a tracking of one of those motions, and you can see the error is within millimeters, and this is done in real time. So now, here is an example of dancing. And in this example, what we are doing is we are capturing the motion, reconstructing the motion, and replaying the motion in different conditions. And here is the replay that is taking place in real time. So now you have those dynamics. You can analyze the dynamics, find the characteristics, and haptically bring feedback, visually and haptically bring feedback to the human to make the corrections. Well, this is an example of a skin stretch device that indicates the angle or indicate a direction. And all of this is going to require, in this synthesis also, to take into account all the constraints and the limitations on the mechanism itself. So to deal with the constraints, we are going to use similar techniques that we use in the decomposition of task and posture and priorities between them. But first, for dealing with constraints, you need to model your robot. You need to detect collision, and to detect collision, you need distances between objects. In self-collision, you need to solve a lot of things. So the problem in collision is not only resolving the collision, but also being able to find the impact forces of not only one object colliding with another, but with multiple points. And this is something that is still in mechanics a very hard problem, that is how we can resolve collisions taking place at multiple points on multi-link systems. Now, the reason this is hard is that we need to resolve this in real time. That is, we need interactive algorithms that allow us to do this resolution. So the way this is done conventionally is going to take this multi-link body. I will remove the joints just before collision, and I do a collision between a large number of objects colliding without the constraints. And then I put the joints after the collision to remove any direction of motion that is not consistent with the constraints. And that makes it very hard. Now, by modeling our robots and systems in task coordinate, we are going to be able to capture that impact force without really going to the full. Okay, we're going to change 1 second. Okay, yeah, that's better. So we are going to make use of those models to resolve the problem of collision, and the way we do it is by thinking about what is really taking place at the collision. So from the collision point of view, it doesn't matter where the feet are, what the left arm is doing. What is important here is what are these inertial properties I have at the impact. And when we have an impact, essentially we are going to be able to resolve the impact by reducing the problem to a problem of collision between two objects. And more interestingly is that when you have the second impact, you have the same characteristic, but also you have the coupling. You remember the matrix lambda. On the diagonal, we have the properties associated with each of the points, and the off-diagonal will give you that coupling. Now you're going to be able to resolve this very quickly. This is an example we did in the I think, late 90s. And it is quite remarkable to see the thousands and thousands of collisions all resolved in real time. So this is also quite interesting now in haptics, because now you can make collisions and you can resolve them and you can create the interaction and you can reconstruct, because you have the model, you can reconstruct the surfaces. I have here an interesting, I think I need my glasses. Let me, maybe it's in the second page. So in here, we are able to resolve, where is it? The control, yeah, here. I have a virtual haptic device I need to bring out. It is, it is somewhere here. It is hidden. Anyway, I don't want to spend time on this, but I was going just to mention that how we're able now to deal with the interaction with even deformable objects, because we are able to resolve very quickly the collisions and the contact. This was applied in ultrasonic imaging, where the robot is interacting through human-guided haptic interaction. Again, we saw today discussions about learning through haptics, and then now we have those models, we can do the collision control. So in self-collision, how are we going to be able to do this without really planning all those complex trajectories? The body is moving away. So it is very simply done through something like a potential repulsive force that would push the body away. But then you start to combine a lot of those constraints, and you are going to have a lot of local minimas. Now, in order to do that in a better, more clean way, what we can do is to say that my task is guaranteed with respect to any motion in the posture, so the posture will not intervene with the task. But how about the task impact on the constraints? If we are able to find a description of the constraint, a representation of the constraints, then we will have a Jacobian. And if we have that description, then we simply take everything, the task and posture, and put it in the null space of the Jacobian, and now we are able to control the task and posture in consistency with that constraint. So this idea is implementing potential field in a decoupled way, in dynamic way, that allow us to create very interesting interactions, and now we can take it further to contact. So when we go to integrating locomotion, we are all the time dealing with this problem of balance. But what is critical in balance, if you are making contact, are the reaction forces. So if you have reaction forces, you're going to tip over. And that is a very difficult problem unless you deal with the constraints itself and guarantee that all the forces applied to the robot will not intervene and create motion along the constraints. So what should we do now? What should we do for the contact constraint? Well, we can treat the contact constraints like an obstacle and say, I do not want to apply forces along that direction. So what is that direction? I take all the normals. I have a description now, which is the description of all the contacts, and then I find the null space of it, take this to the right, put it in the null space of the constraints, and now I have my description, and now I can also control the contact along those directions. So essentially now the robot is moving in its motions, it's not interfering with the contact, and only through the forces it is applying through this first Jacobian transpose F controlling those contacts. So we are building hierarchies, but as we build these hierarchies, we are able to control now the forces, but what is happening to the internal forces? And this is what creates all kind of unbalances in the system, that is the internal forces exerted on the environment by the robot. When you are touching the robot, you're not only controlling the contact forces, but you are also creating an internal force between the legs and the other arm and all the parts that are in contact. So there are moment control. There are 3 moments at each of those contact locations. There are forces, and we model these through a mechanism we call the virtual linkage mechanism. The virtual linkage allows us now to capture all the degrees of freedom that a robot contact with the environment is going to produce in addition to the internal forces. So in a way, what we're doing is we are taking a task, taking the posture, make them consistent, then adding constraints, making everything consistent, and we are building this a unification of the different aspects of the motion in one framework. So your posture is consistent with your task, both consistent with the contact, and everything is consistent with your constraints, as well as your balance. You don't want to fall. So if we take this with one abstraction, you remember these Jacobians, PT, posture consistent with the task. Well, if we have all these priorities all together, what's going to happen, all of this is captured by one point, one single point in high-dimensional space where all the different constraints, contact, and priority between tasks and postures are captured in a consistent fashion with the dynamics of the system, and now all what you need to do is to control that point. So Varia is your representation of everything you want to do with the robot in the environment, including the distance, including what you are touching, including the normals, including all that information. So we go from configuration space to this task consistent, constraint consistent task space. And from that description, what is wonderful is when you have the right representation, you're going to have all the models that you need to control the motion for that representation. Representations are very, very important. So what do? You have Varia, you compute the Jacobian, and from the Jacobian you have the dynamics. And now you have the dynamics in that augmented space, capturing all the different properties, and once you have a model, immediately you have the control. And once you have the control, you are going to find the torques to implement that control. In the case of a humanoid robot, this could work for 2 degrees of freedom robot, directly with J transpose F, and you're going now, the null space is already in your Jacobian transpose here. Now, if you have a humanoid robot, you have an under-actuated system, and you need to deal with the torque in that under-actuated system. So you need to find the relationship between your active forces. You need to take those relations and map them to your whole space. A humanoid robot has 6 more degrees of freedom than the number of motors. So you are projecting with this last actuated torque projection your torque control to maintain all these different characteristics, and that's why you have to be always in balance under all these different forces. Now, when we implement this here, we can see how essentially the robot is moving up and down, maintaining contact, and the contact reaction forces are maintained constant. In fact, I have a simulation of this, I think. So now you're going to see the robot making contact, and as the robot comes to contact, detect the centroid in the hand, recompute the overall centroid of the system, and now the robot is moving in balance. Let me disturb this robot a little bit. So if we, I don't know if simulations are useful or not. I mean, we don't believe that, well, simulations are one part of the problem, but they provide incredible insight in the structure of the problem. But it's not enough. We have to validate. But still in simulation, we can do things that are really interesting. So in this simulation, I'm going to apply a force on the feet, and I'm going to pull the feet up. And you can see the feet is recovering as we apply those forces. And this is essentially a sort of a virtual system that is working and sensing and doing all the proper actions to maintain the forces. In fact, we can try to make it, you can see the corrections taking place. But still, this is not enough, because you really need to experimentally validate, and that is critical in robotics, and it's critical in all physical systems. So here is another example. You can see the robot maintaining the orientation while we're deforming the environment for it. So as we are doing this, what we're trying to do is to span all the different variables in that space. So we are controlling here the virtual linkage, we are controlling the contact forces, we are specifying specific movement at different points. And in this task, if we look at the analysis, so the robot is moving up and down, the robot is controlling step responses in the internal tension between the right hand and the left foot. And it's moving between 0 to 20 Newton. And at the same time, you are controlling different forces. So you can impose all these different requirements you want, but essentially the robot is tracking all these at the same time, because the robot has all those freedoms, and unless you satisfy and make sure that you are controlling all the degrees of freedom in a coherent way, it is not going to produce the right behavior and responses. Now, what you can see is that from everything we are doing is we are unifying. We are unifying the controllers in the space of torques of the robot. That is, we are assuming somehow that we have this system that is going to deliver the right torques to produce the vectors that would allow us to decouple and maintain contact and maintain the characteristics of compliance, and all of these all together in one way. Well, as you know, torque control is not available in most industrial robotic systems. In particular for Ashimo, this was something that was really challenging. How can you control Ashimo with torques? And you do not want to go back and find the trajectories associated with the task and then say, I would like to find the corrections needed for the constraints, and then I would like to find the trajectories or compliances I need for the contact. You really want to find all that balance and apply that torque, and the system will achieve the different requirement. So this basic requirement is essential for everything that we have here in this list and more. But how can we do it? How can we do it for those robots? Fortunately, now we have robots that are being developed. In fact, at Stanford, we started building a torque-controlled robot back in the early 90s, and that brought a lot of improvement to the performance. You know what was the first thing I did when I came to Stanford in 1981? I was to work with the Puma. And the first action I did was to take a scissor and cut the cable of the controller and replace it with a controller that was just a power amplifier to control the current in the motors, so that we can access some sort of torque control. And all what you have seen was just based on an open loop torque control with the Puma to produce almost the torques that you needed for that control. So for this robot, what we did was to create a sort of transformer. We call it the torque to position transformer, allowing us essentially to use the commercial position controller. Here is the transformer. So think about it. You need to produce this torque. In the commercial controller of any robot, at some point, the motor is delivering a torque. But you don't see it. You don't have access to it. But if you know the transfer function, if you know the controller that are being used, you can drive the input and modify it so that you produce the right torque you want to achieve. So essentially what you do is you tell the robot to move to some position, fooling the robot, thinking the robot is going to move there, but actually you are compensating for coupling forces with another joint. And this is done joint by joint. So all of the joints were controlled through this transformer that took a lot of time to implement on all the joints. And then the robot started to move in compliance. And in fact, Honda was quite surprised that this was possible. And the tracking was amazing. I mean, between what you wanted to do and how this is produced, the errors were quite small. So in all of that, what we are doing really is trying to bring the environment, the sensors, the representations all together into the control and producing that torque vector that is going to affect the robot, that will affect the environment and do that change. So if we think about the big picture in robotics, the big picture is you have essentially a system with two blocks, the line of action, and here is the line of perception. You have loops. You're applying torque to the robot, and the robot is going to have encoders and force sensors, and in real time you are running this loop very, very fast. Kilohertz. Now, what you want to do, you want to be able to apply the right torques to descriptions coming for achieving a task, coming from the reasoning about the environment and the planning, so that you are able to bring this robot to execute some sort of behavior, some sort of skill that was described by your planner. Now, what we have done, and what I described here, is the fact that based on the sensory information, we're going to be able to make the abstraction to find the distances, making estimate, and close this loop. And we are closing this actually very, very fast, 500 hertz. In fact, the Varia is capturing all these characteristics, and all what we need is to specify what is the desired Varia. So that means now we abstracted the control to a level of the whole body control. But who is going to bring this Varia desired? How are you going to specify all of these? Now, we do not want the planner to plan all the details of the motion. So this is the idea here about, in fact, building skills and building task primitives that would allow us to plan much more efficiently with the prior knowledge about how a task can be performed. So the planning becomes much simpler, because otherwise, if we wait to build the full model of the world and perceive it and replan everything, it's going to be almost impossible. And however, what we plan, and the human, what they do, they think about feasibility, whether there is a passage, and then I will interactively move through that passage. And that feasibility and that description of a plan requires elasticity in the plan. I'm not going to talk about that, but I wanted really to emphasize the fact that we should not continue to think that we are executing plans of trajectories. We are executing sort of plans involving maintaining constraints reactively. We are executing plans with skills that are there in some library that we are calling and we are combining in our execution. So, as I said, we can develop a lot of things and we can understand much more details about the system when we simulate the system, but we really have to do the experimentation. Here you can see the robot under a constraints, guided by the human, maintaining the constraints, controlling the balancing, and producing that motion. These actually are some recent development with the Ashimo before it broke down. It was done, I believe, around December, last December, and we were able to bring the early implementations of those concepts and results on a robot that suddenly became compliant. And once you have compliance, you change completely the way you program the robot. I mean, what is the biggest challenge that we are facing from the control point of view with those robots is really the fact that we have a lot of degrees of freedom to coordinate, and we think always, let's create trajectories, and let's move the time along those trajectories for the robot. And this is not absolutely the way you can really go to more complex tasks and behaviors. So what we are really trying to do is to think about how we can generalize how we build behaviors and skills that could be implemented in different conditions. So we started bringing motion, mobility, locomotion together with manipulation. And you can see in those behaviors that the robot is performing a lot of other things autonomously, adapting them to the situation of the interaction and the robot behavior with the human. In here, the robot in fact, you can see the hand on the upper arm without sensor. When we touch the tip of the hand, we have a wrist sensor, and we have a different interaction with the robot. There are a lot of aspects of those motions and behavior, and you can see the robot starts to move in a way that is much more natural than those motions that can be rigidly created by tracking specific trajectories. So one last thing I wanted to bring out is this is the Kinect, and we are interacting now with the simulation by moving the robot so through resolving the motion of the human and showing again the simulation and its ability to control the motion. And now the robot will have some fun. Wow. And the human is happy. So I wanted to list all the people who contributed to this many years of work, and I just have some photos of some of them. I don't have all the photos, but you realize this is not a work that was done overnight. I mean, it has been many years of development in that direction of building those capabilities to really take all the constraints together, and many of them are still involved in robotics. Some are involved in more software at Google, and some others started their own companies. So let's go. Thank you very much for your attention. Thank you. Thank you. So Patrick is not here, and I managed to stop well before Patrick brings this down. You never know, it might be automatic. I mean, who knows? So if there are questions, I'd be happy to answer. Yes, please. Yeah, could you come closer, because the room is big for...
So the general idea would be we have a multi-dimensional system, and we would try to reduce the null space of this multi-dimensional system by adding constraints, so we can generalize the stability of the whole system.
Yeah.
That's,
well, I mean, essentially, you have a system with many degrees of freedom. You have a task you want to move the hand to reach. This is 6 degrees of freedom, right? So you have a lot of freedom left. What do you do with this arm? What do you do with the body, etc.? So first, we are able to say what is that space of motion that can be described without interfering with this point. So this point is fixed, and all these other motions. So we have a description, and this is the null space. associated with this. But when we put 2, now the 2 are fixed, and that is the space that is left. When we put the center of mass here, if we want to control it, then I'm really locked. I mean, I can do maybe some other motions, but well, we can try. I mean, so that is the description. Now that is in terms of space, but what we are trying to do is to go to the N transpose, that is the transpose of that space, which connects actually torques. So controls all the joint torque controls, you can apply them directly to control a criteria. How you choose those criteria, I mean these torques, which torques are going to affect this motion? Well, what you do is you take these torques and project them in that NT space associated with that task, and now you are able to control these without interfering with this. And this is the concept that we use for constraints. So when I'm touching something, I have a representation, I have its Jacobian, and now I can do all the motions I want without creating accelerations here. So that hierarchy is null space, projection, projection. Now you can take all of these and put them back in one point, because all of these are matrices, so you can reorganize them, and now you have a task that is much more complex. That is a task of moving while creating a posture that is consistent with that task, all in the same Jacobian. And this that final abstraction of varia. Varia is capturing all the constraints, the things you want to do, and it has to be modified over time. And that's why you need a structure to handle all of those descriptions. But as a result, your description now is in a sort of constraint-consistent task space, and your task is you describe, you can describe what you want in natural language, and it will be translated in terms of those representations. Clear?
Another question.
Yes.
So thank you for your nice presentation. I'm just wondering, like the approach you presented, it statically keeps all the constraints not violated in time. I'm wondering for something fast like running, which you violate the constraints, for example, in the flight phase, and then recover and then violate.
Yeah.
Is something like this possible?
This is a very good question. I mean, demonstration and videos I showed, wasn't showing the robot running. But the way we represent the robot is, imagine you have a link associated here. I talked about it in the under actuation. So move this link up, robot floating. And what we are representing is we are presenting a multi-body with respect to the ground. Now, the motion of the feet is going to be part of that model. So when we are touching the environment, we are looking at an input from the environment on the robot. So in running, we are not changing model. A lot of people take the model with respect to the feet, and then when you move, you have to change model, and when you're jumping, you have a different model. In here, what we are doing is we are able to integrate the reaction forces on the feet, and all the dynamics of the robot when it's running, when it is on one feet, when it is on the tip, so whatever is accounted for. So in this model, you capture that.
Okay, so if I want to complete my question, like when you're using Jacobian to compute things, we don't have any kind of long-term, not long-term, but I don't know, some kind of prediction that we know something will happen, I don't know, two, three steps after that.
Yeah. This is so you remember that control structure. I said we elevated, we abstracted the controller to this level. Now the input varia desired has to be designed to achieve the motion that you want. So the way, this is what you do in your planning, in your skill of running. So a skill of running, I mean, my former student Vicentis implemented running on those models already, and all what it is designing the varia that you input to that system, and then the system is taking into account all the constraints as they are changing and they are modified. My point was that what is important is to have the right presentation so that you can handle locomotion and handle manipulation. So if you are going to touch the environment and push against the environment, it's the same thing. If you are climbing with all the feet and you want to use your body to accelerate, I mean to reach another contact point, it is the same problem. You need to predict how much momentum you're going to build in order to reach there. But all of these are part of the higher level of the planning of the variables that you are controlling.
Just a last short question. So for this, you think it is all possible with like feedback control, something like that, or we also need some kind of trajectory-based feed-forward thing in the middle?
Oh, so by the way, I mean when I said no trajectories, we are not saying we are not using trajectories. What we are saying is part of the task requires trajectory, but the rest of the task doesn't require constraints, and other part of the task requires criteria. So in fact, when we are controlling this F, we are controlling impedance, we are controlling trajectory, we are varying the impedance, we are doing, all of that is beneath. What we are looking at here is the structure that would allow us to input those different things at different locations.